All right. So today we're going to be discussing pressure bulb in foundation engineering, and another one name for pressure bulb is isobar stress. So that is another name for that. So we are going to be looking at that in details. And I'm going to explain the concept. I'm going to define what pressure bulb is, what is the application, what does it help us to do in foundation engineering, and after that we will look at a case study where we have a soil test report for a shallow footing and uh, a pile foundation. That is the soil test. The first one recommended shallow footing, while the second soil test recommended um, a deep foundation, which is pile. So we're going to look at the two case and see what pressure bulb can actually help us to do. Okay, so as if you can look here, you will see that we have what we say understanding your foundation is necessary. Yes, I will also say that again, that understanding your foundation is necessary because it is when you understand your foundation as a science engineer, you will be able to question some things in your foundation. It is when you understand your foundation, you also understand your soil because during excavation on site, it's better how you understand the soil, how you understand how the foundation works. That is when you'll be able to question some designs or some soil investigations or soil reports that will be sent to you. Then, as a structural engineer, understanding your foundation will also make you design a realistic uh, design. So far we have been talking about foundation. So if you check other videos of this channel, you'll see that we have talked about the raft foundation, that is the different types of rafts, the slab rafts, the beam slab raft foundation, both the upstand and downstand. We also have talked about the piled rafts, that is a pile with a combination of what rafts. So we also went on to discuss about the what does the cohesion value of a clay soil tells you. We discussed about that and the other videos as well. So you see that the main aim at the moment now is to make sure that we understand foundation, we understand our soil. Okay, so let's go into today's business. All right, what is a pressure bulb, or otherwise known as what stress isobar? Okay, so it's basically a geotechnical term because it deals with the foundation. Yes, it talks about the soil behavior. And geotechnical engineering is a field that actually discusses about the soil and foundation as well. So as you can see, the isobar is a tool used to visualize how a structural load applied at the ground surface disperses what vertically and laterally into the underlying soil mass. So from that definition, you have to take a keyword, the conceptual word tool. So it's that is something that helps us to understand or do something, right? Because a tool is something that is used to achieve a particular thing. So actually, a pressure bulb is a conceptual something, and that is used to what visualize. Another thing to mark out here is what to visualize what structural load. You want to know the behavior of a load on on the soil or at the ground surface, depending on where your foundation or the depth of the foundation is being what terminated. So we use isobar, stress isobar or pressure bulb to know how the to visualize the structural load, how the load disperses vertically and laterally into the dimension. So what he's trying to say is that when you apply a load, or when your foundation, your footing sits on the soil, we want to know at what depth of the soil will express this load I applied. If you tabulate your footing at 1 meter depth, do not assume or do not think that the effect from the load will be felt only by the soil immediately under the footing. No. Some soils deeper will also experience that stress. Okay? So, in the sense that once you apply a load, once your footing is there and your building is loaded, and there is a load transfer to the footing, you discover that if you have um, a footing at 2 meter, so you see that from that 2 meter down to about 5 or 6 meter, we still feel the effect of the applied load. That is a vertical movement, and also in the horizontal or lateral movement. The surrounding soils as well, we have an effect. So the pressure bulb will now tell us at what depth will you have a soil, or at what depth with that, or at what depth of the soil will experience that force or that load. And when you draw this isobar, you can have a picture. Okay, so that is what the stress isobar or the pressure or bulb. Okay, so then essentially a pressure bulb is a three-dimensional imagery surface that connects all points in the soil where the vertical stress is equal due to an applied load. So we have explained that is a diagram that actually shows the soils that actually been affected by the applied load. Okay, and it means that each isobar line, when they mean vertical stress is equal due to applied, where the vertical stress is equal, it means that each isobar line has equal what stress. Then also, when you look at another word here that I didn't explain, it talks about disperses vertically. Disperses is another keyword. Means that as you go down, the soil, you discover that the amount of load being felt will become lesser. Let's say you have the footing at 2 meter, then the one immediately at 2 meter, we feel the much stress. Then the one at 3 meter, we feel less stress than the soil at what 2 meter. The one at 4 meter, the soil at 4 meter, we feel lesser stress than the one at 3 meter. So that means what it means disperses, and that is the what isobar helps to do, to know which of the soil, the depth of the soils that we feel this pressure. All right. So then, so as the stress increases, the stress intensity decreases with both depth and radial what distance from the point of application. Okay, that's what I've explained. So you see that as you go down the depth, the stress will be what reduce. Then as you go horizontally or laterally, the stress will also reduce. So understanding the pressure bulb is critical in geotechnical design as it provides a framework for evaluating how stress distributes under footing, raft pile, and other foundation types. This in turn informs decision about foundation size, depth, spacing, and soil exploration what requirements. So just as explained, this is, remember, we from the definition we said is a conceptual what tool, and the tool is what you use to achieve a particular thing. So what do we achieve by using the isobars? And that is what you have been told here, that we use this to make decisions about foundation size. And that is when we study a case study for, there's a case study for a soil test report. We will look at how that will govern our foundation size, then the spacing, especially in pile, and also helps in the depth of what soil exploration. When you want to carry out your soil investigation, what depth should you terminate your boreholes? So you see that the pressure bulb also helps in determining that as well. So as you can see from the diagram, we have the applied load in yellow color. Okay, then we have the stress isobars, that is the orange color. Then we have the zone of influence. The zone of influence is the zones or the soils that experience the effect of the applied load. So the influence is the zones that would experience the effect of the applied load. Like where you said the zone of influence is area where load effects are significant. Alright. Then the green color is the foundation design. So where this is where you now determine your decisions on size and depth. Yes, because depth is also very important. Where is from the pressure bulb. That's why it is said that most times it is not good to dig or to excavate more than the what specified depth, because we might be causing a lot of problem. So we are going to look at that as we have a case study where we see where depth is being have to be very what careful in terms of excavation. And also you have to be very careful in your size of what excavation. So you see that it is it is very important for a structural designer or a structural engineer when he's designing his foundation, because you have to be very careful of the size of footing. And also for a site engineer, you have to be very careful in monitoring them not to excavate more than what required. But once you don't understand this pressure bulb, you will not find it you find it difficult to comprehend or to even understand why you should not excavate than the specified depth. So the next question is, why these pressure bulbs? Why is it important in foundation engineering? And the first thing here is how deep the soil should be explored during site investigations. So let's say, for example, I'm having a footing of I have a shallow footing. Let's say we have a shallow footing. So, and you are being called as a geotechnical engineer, like just to carry out a soil investigation. From the pressure bulb, you'll be able to know, okay, this is the depth I'm going to terminate this is the depth I'm going to terminate that. And we are still going to show you later in the video how this can be determined. So, but you just have to know that from the pressure bulb, you can say, okay, I need to terminate my borehole at so depth, or terminate at this depth. Then another importance is where settlement may occur and how it could affect structural what performance. So from your soil investigation, after you are giving the report, you look at the soil profile. So from there, from the pressure bulb, you now be able to know, okay, this is the zones or the zone of influence. These are the area of soil that are going to have a significant effect. So you now look at it. If the soils should have this effect, will they be able to? Are they? Is it a good soil? Can it? Is it going to settle more? So you see that if your zone of influence now enters maybe in a soft clay, you see that you're going to have settlement problem. And once that settlement problem, your building begins to what tilt towards a particular side. And that is where they said why they said is important, because you must, from the pressure bulb, you know that okay, if this should get to this point, I'm going to have a settlement problem. And also from the pressure bulb, you're able to know between between the two footings, am I going to have what we call an interaction between the two footings? You know, one of the problems that you that occurs when the foundation overlaps, that is the pressure bulbs of two foundations overlaps, is that these two foundations will now begin to interact. And once they begin to interact, then there will be a reduction in the what? In the structural capacity of that foundation, which you don't want that to happen. And especially it is more in pi foundation, where we normally say that the spacing of two pies should not be less than 2.5 d. So why these rules were set is because you don't want an interaction between two pies. And once there's an interaction between two pies, you have to be very careful because the structural integrity will be what's compromised. Okay, so with the pressure bulb, we're able to know that okay, these two columns or these two foundations with their pressure bulb overlap. And once there's overlap, you need to begin to space it a bit. Okay, another important thing is that we also have from the pressure bulb, we're able to know the amount of stress that is being carried by the soil layers. Each of the soil layers, we're able to know at 3 meter what is the amount of pressure that is there. You can determine that, yes. Then also at 5 meter, what is the amount of pressure there? At directly under the foundation, what is the amount of pressure there? You can also determine that as well. So, and that is why we have here an example that says if a structure is built on shallow foundations and a layer of soft clay lies within the pressure bulb, it can result in excessive or uneven settlement. This may cause cracking, tilting, or even failure of the structure. The issue is especially critical in urban areas where buildings are often closely spaced. So, from what I've said so far, you can see that as an example given, the pressure bulbs are found within the what or the zone of influence are found within what a soft clay, and you know that soft clay can't handle much of what can't handle what much of a settlement. So if settlement happens, you have your cracking, you have tilting of the buildings. So that is why it's very very important. So and when you look at this diagram here, you can see the pressure bulb for a point load. This is the pressure bulb at different depths. This is the pressure bulb at different. So this is isobar lines. This is the line of the pressure bulb. So you're not saying that along this line the pressures are what equal. Along this line as well, the pressures are equal. But this one will be lesser than this will be lesser than this will be lesser than this. But along the lines, they are equal what pressure. So and from the also this diagram also explains the importance of foundation of a pressure bulbs in foundation engineering, and you look at the predictable soil behavior. You give an informed decisions. Stress impacts structural what integrity. So it helps in determining the exploration depth, settlement, and assess interaction between foundations, evaluate the stress in each soil structure, and that is what I have just explained. So one of the persons that worked on this is called Bosinesk. So he's one of those people that worked on this, and he gave a simplified formula. So and this formula actually estimates the vertical stress at a particular depth. Also, um, you can also estimate the depth if you know the stress as well. So this is the formula or the mathematical equation that is used to estimate the pressure isobar. As you can see, this pressure isobars, it was obtained using this equation. So, and what does this equation actually tells us? So, from the equation, you see that the stress is directly in proportional, or is sorry, not directly, but indirectly or inversely proportional to the depth. So, as you go, the deeper you go, the stress will also what decrease. So, and I said that the closer you are at the point, you are to the point load, the higher the stress in the soil. Then as you move deeper and you move if you move away horizontally, the stress also was decreases, as you can see from the formula that both the z, which is the depth, and the r, which is the horizontal distance from the applied load, if increases, the pressure will also what decrease. All right. So let's say you have a depth, you have a load of, let's say, 500. You put your 500 at the depth of let's say 3 meter, and maybe a horizontal distance of 0.5 meter away. When you put it into um, this formula, you have a pressure, and for you to draw the pressure isobar, it will have to be from the tip or the edges of the footing. You take a curve. You take a curve. So this is at the tip of the footing, and you take a particular curve, then indicate the value of what the pressure. So now let's look at what we know. How does it have, what does it say about your shadow footing and what your piles? Likewise, the rafts as well. Okay. So apart from using this, maybe for those who are on site, you might say, okay, how can I do this? How can I do this when you're on site? There's also a quick way of checking. There's a rough estimate of checking the zone of influence. So for a spread footing, the depth of significant stress, that is the zone of influence, is usually estimated between 2 to 3 times the foundation width. So let's say you have um, a foundation width of 2 meter. So you are going to do 3 times 2. If you want to check the maximum, because it's usually between 2 to 3, so you want to be safe, you check the maximum. If you say 3 by 2, that is going to give you 6 meter, and you have your foundation terminated at 1 meter. So you see that from that 1 meter down to 6 meter, those soils and those zones are going to have feel the significant effect. So in that case, you now have to check what type of soil do you have at that particular depth, how is it going to affect your foundation. So this is a quick way of estimating the depth of zone of what influence. Okay. Then for a pile, and you can see the diagram here, this is for point load under a shallow footing. Okay. Then this is for a pile. Pile actually works with the side friction or the shaft friction and the end tip, which is the end bearing. So in that case, the pressure bulb tends to be what narrower and deeper compared to the footing that is more broader and more bigger, right? So if I want to know the effect or the zone of influence for a pile, for the end tip, for the end tip, because the diagram has to be made from the tip, you have a curve. Like just like as the footing, like we saw here, this is from the footing, we have a curve. But when it comes to pile, you see that the load or resistance to the load is not only by the end of the tip, but also by the side of the friction. So for the tip alone, the zone of influence will fall within 5 to what 10 D, and the D is the pile diameter. Okay, so if you have about let's say you are using a pile of 600, so 10 by 6 is about what 10 by 0.6 is about 6 meters. So if you want to estimate the horizontal effect for the side for the skin friction, you can use 1 to 2 T. So you're able to know the zones of influence. And that is why in your pipe foundation, the recommended depth is always 2.5 D and above. That is the spacing between your pipes that are in group, or even they are not in group, but the spacing should not be less than what 2D. Because once the spacing is less than 2D, according to this now, you see that your piles will begin to what interact. The pressure isobars will begin to overlap, and once it begin to overlap, it will reduce the pile capacity, and that is why it is being said that your pile spacing should not be less than what 2.5 or should not be less than 2, according to some articles. So it always be better not it for it not to be less than 2.5, because since you are giving this, you will be safer by taking 2.5. Let that be the minimum spacing of your piles. Then for the mat or the raft foundation, you see that is a very large footing compared to the shallow footing. So the loads are evenly distributed, and the effect or the zone of influence doesn't go that deeper, right? So that doesn't have much of a problem. Then though we are given this is for simplification, but it has a limitation as well. Okay, both models assume an elastic, homogeneous uh, soil. So you see that this theory assumes a homogeneous and elastic soil, but in reality, it's not homogeneous. We have a heterogeneous what soils. So in reality, the pie shaft generates shear along the wall. This produces some additional vertical stress. So, but you see that this person's theory is just a simplification. But in case we have when you have a groundwater or you have a consolidation effect, actual settlement might exceed what elastic conditions. So you see that the limitation of this this Bosinek's theory is that he assumed a homogeneous and an elastic soil. But once we have a groundwater or consolidation effect, you see that settlement is no longer that elastic conditions. All right. So now let's look at a case study. Let's look at a case study. So this is the soil profile for this soil test, and this is the depth. Okay, this is the depth, and this is the thickness of what the soils, and this is the n value. This is the n value, and a recommendation says that at a depth of 3 meters and a size of 2 by 2 meter isolated footing and safe bearing capacity of 18 tons per meter square can be used in sand with n value greater than what 23. So that is the recommendation from the soil test report. And when you look at the n value, you will see at this sand, the black sand, we have it to be 2, telling that it's a very weak soil. Then the one mixed with clay has also 3, telling you also is a weak soil. But now, when we come to sand, the white sand, we are having our n value of 23 and 24. But when we get to a sand, we are having 50 for the n value. That is to tell you the n value tells you the amount of resistance given by the soil. So the higher the value, the higher the resistance. So, but now after the 18-meter depth, after 18-meter depth, we now have what we call a sand mixed with clay, and that eventually reduces the capacity or the strength of the soil. So you see that it has 3 and 2, which is the same property with that of what the first one. So because of this, the the geotechnical engineer gave an instruction that if you want to use a shallow footing at a depth of 3 meters, because it is at 3 meters that we have a stronger soil with n value of what 23. So it is recommended that the foundation should be at that position, the foundation depth. So in not saying that if you want it to be at that position, at that particular 3 meters, then you should also note that your foundation, your footing should not be what more than 2 meters. Okay, so let me do some calculation. Okay, so now for a footing we are told is the zone of influence, that is the soil that will feel this impact, is going to be within what 3b. So then when we come back here, we have 2 by 3 because the footing width is what 2 meters according to recommendation. We multiply by 3, so you're going to have 6 meters. So you see that from 3 meters where the foundation is or where the footing is to a depth of 6 meters will fill the path of any load that is coming. Okay, so from this 3 meters now you add extra 6. So that is at a depth of what 9 meters. That is at a depth of what 9 meters. Okay, so that is at a depth of 9 meters. So now um where do you have 9 meters? This is 5 and this is 8 points. So you're going to have 9 meters at this particular point. At this particular point. Okay, so let's try 2 by 2. 2 by 2. So you're going to have 4 meters. Right? You're going to have 4 meters. So and the 4 meters plus 3, that is about 7 meters. So you see that the zone of influence falls at this sand here. So the zone of influence falls at this point. So you see that it's still within the zone of what good soil. So the investigation, the man that gave the instruction used um excuse me. So the man that gave the whoever that did the investigation used the minimum, which is the 2, and that's when he gave the instruction. So but if you use the 3, you might be into this zone. If you use the 3 to check, you might be in this zone. And when you use 3, you are being what safer compared to when you are using 2. So you see that the 3 went down to 9 meters, 9 meters at this point. So but then let's say you are using 2, we are using 2 as the geotechnical engineer have specified. Let's say we now ignore the instruction of maintaining 2 by 2 meter. We now want to maintain 3 meter by 3 meter. And when we do that, we have 3 by 2. We are going to have 6. And that 6 falls within the clay sand with a bad soil. So in this case, don't be surprised when you begin to experience or begin to have excessive what settlement, or when your building begin to tilt and there comes crack because you have let your zone of influence to actually encroach into this bad soil. So from here now you can see the importance of um sorry. So from now you can see the importance of what pressure bulb, because here we talked about it helps inform what decisions about foundation size. So we from there the geotechnical engineer has now said giving us a particular size. Then from there he also gave us an insight or informed decision where the foundation should be what terminated. Okay. So and also from the soil test report, you discover that they terminated their investigation by 12.5. Okay, and you can determine that by using this formula. A way of doing that, for example, you can let me get a calculator. Example of doing that, you can do this. Let's say, for example, you are saying that for a duplex, just a one suspended floor, for example, now that is the type of building. Because I believe when you want to do an investigation, when you meet a geotechnical engineer, he's going to tell you that okay, what type of structure do we have? So let's say we have a duplex, okay, and within you now said okay, there is no way a load coming to a particular column with more than 1,000. Yes, just a normal residential duplex, not a factory or an assembly building or something. You understand? But just the residential what duplex. If you said okay, there's no way the load is going to be what more than 1,000. So if our load is 1,000, I'm going to have 3 by 1,000. So okay, 3 by 1,000 divided by um so divided by one multiplied by 1,000. Okay, divided by 2. Sorry, what am I doing? 3,000 divided by 2. Okay, divided by um pi, then divided by let's say you just take a depth of 7 meter. Let's say a depth of 7 meter, or a depth of 7 meter. Let's take 7 meter, and 7 square is 49, right? So divided by 49. Okay, so then we are assuming that the point of consideration is directly at the center of the load. So if we are looking at the center of the load, that means the horizontal movement will be 0. That is, your R will be 0. When you put the 0 of R here, everything here turns 1. And once it turns 1, you have just this formula. So you see that at 7 meter, we are having a pressure of 9.7. To you, is it a significant pressure? Is it a pressure you should be worried about? Then, if it's a pressure you should be worried about, increase the depth to like 10 meter. What pressure do you have? Until you get to a point that the pressure becomes what? Negligible. In that case, you can say, let me terminate the borehole at that point. But also, I'm just saying, based on this, you can also get more information from a geotechnical engineer. They will be able to give you the accurate information on how to, on one of those things they consider before they now decide where to terminate the borehole. All right. So, having said that, this is a case study. Then, likewise, this one as well. Likewise, this as well. So, according to this, sorry, it was not written, but I just brought it out as an example. According to this, it was recommended that the pi should be terminated at 18 meter. The pi should be terminated at 18 meter. Okay. So, and according to this soil investigation, we have only information about at a depth of what 22.5 meters. That is where we have information about the end value. But when we come here, we don't have further information. Okay. So, but at 22 meter, and from the what we have here, we were told 5 to 10D. Okay. So we are having 5 by, let's say you are using or let me use 10D actually. We are using 450 mm diameter of pile multiplied by 0.45. So you have 4.5. Okay, so when you come to this, so when you come to 18 meter here, you add 4 to it. So we have um 4 plus 18 is going to be 22, and we have 4.5, so which is 22.5. So you see that this zone will experience the we have what we call the zone of what influence. So nothing concerns us at this point. But what if you use a pile of 600? You discover that if you are using 10, you have let's see, 10 by 0.6. So you have 6 meter plus 18. That is going to be 24.5. And now let's say you use 8. So you have something about 22.8, which is almost the same thing with that, or 22.5. So by so doing, you can now look at some reports, some soil test reports, and see if there's a mistake from it. Maybe you can call back the technical engineer if it's an oversight or something, or you can just say maybe after your calculations you discover that okay it's going to be around this place. So you can call the geotechnical engineer that okay please is there a way we can have information about the soils below or the soils at this particular area. So this is how you detect some errors. All right, thank you for listening, and also please remember to drop your comments in case you have any contradictory uh, thing about what I've said, or you have any other thing to contribute. You can also put down in the comment section. Remember to subscribe, like, and share. We are just getting started. We are just getting started. We always make sure that we explain these concepts that is very necessary for both students and professionals. Remember that understanding your foundation is very, very necessary.